All right, it's 9.7. So we're going to be talking about the different ways we can basically describe where we are in the coordinate world realm. Okay, so most of our lives we talked about things like x and y, or x, y, and z, or even x, y, z, and w. These are what we call rectangular coordinates. For all intents and purposes, we might as well live on a flat box, because in our normal daily lives, most of us, we live on a flat piece of ground. We live in a rectangle. We hang our pictures on a wall. We walk on a flat floor. Most of the things we do in life, this works out real nice for. Real nice. Okay? And there's a whole lot more to say to that. We are very familiar with this. I don't know. I really don't need to belabor the point. However, once we get out of ways, we start talking about, we talked about polar coordinates, you might remember back in the day. Of course, as soon as I start recording, everything starts acting up here. Anyway, these are known as r and theta. So you tell me how far you go and in which direction, please. Okay, so for instance, I could say I want you to go 5 units at 83 degrees. Awesome, let's do it, yo. Boom, here's 83 degrees, and we're going to go out 5 units. 1, 2, 3, 4, 5. Oh, that's great. That's awesome. That looks terrible. Anyways, what I was saying was, there it is. Now, we are out 5 units. 1, 2, 3, 4. There you go, 5 units at 83 degrees. Now, can you convert that to rectangular? Sure. Just drop this line down, and you're like, oh, dude, no way. That's 83 right there. Yep. And so literally you'll just go 5 cosine of 83 and 5 sine of 83. And then you are home free. Boom. Now, I will say this. Make sure when you're playing this game, make sure you're going back to degrees. You will thank me. All right. What are you doing, you jackass? .609. Idiot. 4.96. And yes, it is that easy. X is simply equal to r cosine theta, and y is simply equal to r sine theta. It is that easy. Can I go the other way too, Jay? Can I? Can I? Can I? Please? Yes? Of course you can. Don't be ridiculous. So, here's the game, obviously. To get r, you're going to do, it's the square root of x squared plus y squared. That seems straightforward enough. Here's x, here's y. That's Pythagorean theorem. There you go. Piece of cake. How do I find the angle theta? Well, here's my deal. Okay, it's the arctangent of y over x. That's true, sort of. Okay. Keep in mind, you have to remember what quadrant you're in. Now, of course, there's the classic. Anytime you're dealing with the arctangent, you have to memorize that ginormous rule. Or you could just go, wait a minute, brah. Check it out. So arctan of, in this case, it was 4.96 over 0.609. Boom. And that comes out to be 83 degrees. And you're like, cool. Wait, am I in the first quadrant? Positive. I sure am. All right. What if it was negative and negative? It would still come out to be 83 degrees. But then you go, wait, am I in the first quadrant? Dude, I'm not in the first quadrant. I'm down here in this quadrant. Well, cool. So it's going to be 83 degrees, which is from here to here, plus 180. All right. Plus 180 if that were true. Okay, 263. So pay attention to what quadrant you're in. I don't really want to, there's a bunch of goofy ways you can memorize it. It's just easier to figure out, hey, what quadrant am I in, and go from there. Let's try one, shall we? Suppose I told you I was in -3, 2 for my rectangular coordinates. 1, 2, 3. Boom. There you go. Boom. What is my r? Well, that seems fairly straightforward. It's a square root of 9 plus 4, square root of 13. Beautiful. So it's the square root of 13, comma. All right, let's go find that guy. So arctangent of 2/3 negative Negative 33.7 degrees. Whoa, bruh. That's down here. That's weird. What do I do to it? Tell you what I'm going to do. I'm going to add 180 to it. Puts me at 146 degrees. Good enough. Okay? That's it. That's all there is to it. Now, you're like, wait, what if it was, in fact, this guy? Well, if it was, in fact, that guy, what you would find is this. You're like, oh, it's negative 33 degrees. Ooh. It's not how we write it, though, bruh. So we need to get, we need to get from here all the way around to there. So we're going to take negative 33.7, and we're going to add 360 to it. And so it's going to put us in at 326, or thereabout. 326, you jerk. 326 or thereabouts, right? Because we went from here all the way here is 327 or whatever degrees. Does that make sense? You got to come at it from the standard position. Now you're like, well, that's cool. So polar form is our theta. That's right. Wait, well, and that goes, of course, with our xy up here, like something. Yeah. Which is, of course, rectangular. But what about if it was in 3 dimensions? Oh, I'm glad you asked. Okay, well, if it was x, y, z, again, that's rectangular. Check this out. We're simply going to go r, theta, z. This we call cylindrical. And we call it cylindrical because if you think about it, you're going to trace out a circle down here, and then you're going to come up a certain height. Okay, that's a terrible rendering. Let me try to draw it from the side. There's your circle down here on the xy plane, and then you come up to here. So if there was your initial, that was standard position, you're going to swing it over a certain ways, and you're going to go out a certain distance, and then you're simply going to go up from there. It would trace out a circle when you get done drawing it out. So in essence, if I said to you, listen, I want to be at 3, 2, 5, and I want to go 2 cylindrical, I would literally go, well, I don't know what it is, but I know it's going to be 5, because it's the same z. That's it. Boom, boom, done. All right, that part's easy money. So, oh, let's still do 3, 2 again. That's lame. That is lame, brah. Yeah, let's do that one. No, that's much, much better. I don't know if it's better. It's different. So here we are. So you're like, all right, cool. So the square root of 16 plus 9, why, that's 5. All right, so 5 is my radius. And my theta, 1, 2, nope, try again, stupid. 1, 2, 3, 4, 1, 2, 3. Ooh, we're in quadrant 4 this time. So arc tangent of negative 3/4 negative 37 degrees. Well, that's not helpful. I need to get from here to here. So I just add 360 to that. So 323. These are two ways of describing the same place. And again, why would I want one versus the other? Okay. Now, polar form, of course, is that idea of a radar screen, kind of that idea that, hey, this plane we see coming towards us has a certain elevation, a certain altitude. Okay. And from where we are, they are, out 20 miles on, at a 270-degree compass heading from where we are, whatever it happens to be. That's that idea. There are other places where this might shine, but a rectangular coordinate system wouldn't mean anything in that case. That's just weird. That's just weird. As, of course, as you know, as you're flying, obviously altitude makes a huge difference, but also that concept of, you fly across the roads at a goofy angle. As the crow flies, as we say, we're going to go from here to there. Where we're going, there are no roads, all right? And so the idea of a grid or a rectangle makes no sense. You just point it in the same direction and just go, okay? And it's pretty straightforward. Again, not too bad. Going the other way, it's pretty straightforward too. If you had 7, 130 degrees, and 2, let's do negative 2 just for a good time. Awesome. And I was going to go to rectangular. Well, the first thing I would do is write negative 2 because the z's are the same. And then I would simply just go, excuse me, I'm going to die. I guess if you're really hearing this video, I didn't kick the bucket choking to death on something. There you go. Give it to me. -4.5. That's my x. And then, of course, (5.36). Okay. Notice that the sine, that 130 is in that second quadrant over in here. So your cosine will be negative. Check. Your sine will be positive. Check. Nice. That's awesome. Okay. Now, again, we are actually below the second quadrant, if you think about it, because our z is negative. Okay. And so it's kind of cool. That's the game. Technically, there's 8 octants. Okay. The first octant is the x, y, and z are all positive. Okay. But after that, we really don't name them. So don't get all weirded out about that. And the last one is spherical. Now, obviously, this one doesn't have a two-dimensional version. Okay, there's really no way to do that. That's just weird. Okay, and so what ends up happening is this: you tell me rho, theta, and phi. Whoa, is this the same theta from cylindrical? You know it is. It is. You're right. Good job. And so that's going to be a big deal. Okay, remember we have x, y, and z. And of course we have r, theta, and z. What I want you to really focus on is these guys share this, these guys share that, right? So if you think about it, you're like, well, is it easy to go from here to here? It's doable, but it's not as easy, but it is doable, okay? Don't get me wrong, it's not impossible, it's just not as easy. Typically I give you one and I want the other two. So typically if I gave you, for instance, this guy, well, I'm going to go probably to cylindrical first, and then from cylindrical work my way back to rectangular, or vice versa. But I'm probably not going to go straight from spherical to rectangular, because that's just, it's weird. Now, interestingly enough, you're like, oh, that part there, that part's easy. It is. Okay, so check this out. So x squared plus y squared plus z squared is equal to rho squared. Okay? Or in other words, this is true. In other words, rho is the straight line distance from the origin out to the coordinate. Wait a minute. Are you saying that it's the radius of the sphere? That's exactly what I'm saying. That's what rho is. Rho is the radius of the sphere. Okay? Which literally this is the definition of a sphere, right? Is that that the distance from a point in 3 dimensions is that value right there. Okay, now you're like, wait, I know how to find this guy. This is of course just, or theta rather, is equal to the arctangent of y over x. Sort of, again, accounting for which quadrant you're in, obviously. And then, well, what the fink is phi, Jay? We'll get to that in a jiffy. Okay, I promise. It'll be good times. Now. Pretty easy to do. Something I would like to mention is this. We know what r is. We know that r is equal to the square root of x squared plus y squared. That's true. But wait a minute. Doesn't that mean that r squared is equal to x squared plus y squared? Well, it does. That means that rho is equal to the square root of z squared plus r squared. Ooh, it does. Wait a minute, though. That's weird. Because I feel like that means that r, which is down here in the xy plane, and z, which is obviously z, that means that rho is the hypotenuse of those guys. And that's exactly right. That's exactly right. So what we're going to have is this. Viewed from above, looking down at the xy plane, this is the x, this is the y, you're going to swing over theta, wherever it is, just like we did before. We're going to swing over theta. And then we're going to march our little fannies out to here, and then we're going to climb straight up, and you're like, oh, okay, cool, here I'm above the page somewhere, Jay. And then we're going to draw a line from the origin up to that spot that's above the page. That's right. And you're like, oh, that's my phi, or my rho. That's right, that's it. That's all there is to it. And so you're like, well, that's not too bad. It's not too bad. Now, keep in mind, this would be the origin here, right there at that point. Now, if I were to come up here like so, this is the vertical. phi is this angle right here. Okay? And so if you think about it, that means this guy here is also phi, because this guy and this guy are parallel lines cut by a transversal. Alternate interior angles are equal. By the way, don't ask me to do any more geometry than that. It's about tapped out at that point. But if you think about it, what's the relationship here? Well, I feel like the cosine of phi is equal to z over rho. So in other words, z is equal to rho cosine phi. Look about right to you? Feels about right to me. Nice. That's great. That's awesome. All right. Now, interestingly enough, is there a relationship between r and rho and phi? And there is. Turns out that r is equal to rho sine phi. Can you see that? Okay, obviously from that triangle right there. This is the opposite side. Wait a minute, though. Wait a minute now. I feel like when we did this before, we said r cosine theta is what x was before. That's right. Wait a minute. Could I just substitute this guy in here? Yeah, you can. So it comes x equals rho sine theta, or I'm sorry, I usually write it this way. Rho cosine, I usually do cosine theta sine phi. That's what I normally do. Y will be the same thing, except remember that y is equal to r sine theta. So I usually go r, oops, I'm sorry. When I substitute, I go rho, then I do sine theta sine phi. And then z is equal to rho cosine phi. That's the conversion. You do you, friend. I don't care. We'll get there either way. Those are the conversions. Now, let's do some examples, shall we? Let's do that. Let's do -7, 4, 9, whatever. This is rectangular. Let's get the other two. What do you want to do first? I don't care. Let's just have fun, shall we? Okay. So let's go cylindrical first. That seems easy. Cylindrical. Bam. I got dibs on the 9. Okay, I've did my part. So r is equal to 49 plus 16 squared. Indicated. That's a square root of 65, looks like. And then theta is the arctangent, sort of. Don't forget the sort of part. Don't screw that up. Okay. Well, just one of them's negative, you goofball. There you go. And so the arctan of -4/7 is -29 degrees. Let's see if that's what we want. So -29 degrees is right here. Well, look, we're in 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. We're up here. That's not what I want. So I want 180 plus that. So done. 150 degrees. Boom. There's your cylindrical coordinates. Piece of cake. You're like, ooh. Now let's go to spherical. Whatever. Cool. Let's do that. So if I'm in spherical, right off the bat, I got dibs on the 150 because that's my theta. Boom. Right now. Right now. All right. Cool. How do I find rho? Well, again, rho is a squared b squared c squared d squared, right? Here we go. So that's going to be 49 plus 16 plus 81, right? To the 0.5 power, I guess. So 12.08. And then, how do I find phi? Well, recall that z is equal to rho cosine phi. Well, I know z is 9, and I know rho is 12.08. Therefore, I should be able to find the cosine of phi. The inverse cosine of that, what are you doing, you weirdo? Inverse cosine of 9 over 12.08 becomes phi. About 41.8 degrees. Okay. A couple things to think about. Theta can go from 0 to 360. You can go all the way around. That's true. Phi is a little different. Okay, so the way I like to think about this is like, wait, two angles, a sphere, two angles, a sphere. This feels like latitude and longitude because it kind of is. So theta would be equivalent to your longitudes. That is, if you were here, if you were in Great Britain, you were in the 0 degree longitude one, and you'd work yourself back around, and like us over here, we were at the 122nd degree west longitude. And it's that idea that we went around, in other words, if this is your main circle right here at the equator, and like you were there, you spun it this way 122 degrees to get to us. Okay? And so, roughly, okay? Somewhere in that ballpark anyways, okay? So, theta is that idea of the xy plane. So, if this were the xy plane, that's what it would be looking like, okay? Nice. Now, the difference is that phi, you're like, oh, it's latitude. Nah, not so fast, Haas. It's 90 minus the latitude, basically, in the northern hemisphere. Okay? So, normally we start here and we work our way up. So, 0, 10, 20, and so forth. Well, that's not how phi works. Phi starts at 0 up here, and it floats all the way down to here, 180 degrees. So phi always goes between 0 and 180. Okay, technically not equal to 180. The idea being, of course, is that you start at 0, that's pointing straight up. You just drop it down to whatever angle you want to drop it down to. It's the angle from the vertical is what phi is. Now, could you technically do 180? You could, but you could just as easily say you had a zero. If it was 180, it was just basically straight down then, right? It's just straight down. And what would your theta be? Well, it'd be 0. And what would rho be? I don't know. Let's say it's 10. Well, then what are you going to do? You're going to straight down 10. So it could be 180 with a positive 10. Now, technically, it could be equal to 180, I guess. You could just say it was negative 180 as well. Okay, I think you said negative. You could say negative 10 as well, but we typically don't do that because it's in distance. So you could go to 180. But it's a pretty straightforward deal. Now, what I normally do in class, I normally do little motions for you. I stand here like so. This is just awful. Here's my hand up in the air like so. Okay. Nice. And then my tootsies are pointed along the x-axis like it normally is. Okay, I just like it along the positive x-axis. It's the positive x-axis. This is how I like to envision it. Okay. Let's make. And then that up there is the positive y-axis, okay? So I'm going to twist. So my tootsies are now pointed in the direction of my toes are now pointed. That looks weird. Well, I don't care. I'm going to do it anyway. I don't care. This is why I suck at drawing, okay? Now, my toes are now pointed in the direction of theta, if you want to envision it that way, okay? Now, but notice that the origin is actually my shoulder. This is the actual origin. This is my origin here. Because the next thing I want you to look at is that my arm is phi, or rho rather. The length of my arm from here to here is rho. Okay, so what am I going to do? I'm going to rotate over to theta. I've already got my rho picked out. It's my arm length. This is for visualization purposes only. And then now I will roll my arm forward. This is the vertical, obviously. I will roll it down a certain amount phi. So that from here, this is 0, 0, 0. This is my point out here. It would be something like, well, it would be rho, theta, and then phi. And that's how I model it. Normally, you make a big deal about it in class. It's a little trickier to do not in class. I could model it for you on camera here, too. But you'd be like, that makes no sense. I can't see what you're doing because, you know, and it's the video, and the video is not great, obviously. Here's another example. 30, 125 degrees, 7. And I'm telling you right now, this is cylindrical. Pretty sure it was cylindrical anyways because only one of them is a degree. Hey, I need to have a rectangular. That's cool. Hey, I need to have spherical too. All right, whatever. Me personally, I'm just going to jump in and put out some of the stuff that I know. These guys share 7. These guys share 125. Beautiful. Beautiful. All right, let's have some fun. Okay? Now, I know that to get to rectangular, it's simply going to be 30 cosine 125 and 30 sine 125. Let's do it. Negative 17. Wake up. Don't go to sleep on me over there. Oh, for Pete's sakes. 24 and a half. Whatever, okay? There's my rectangular components. That's nice. And again, how do I get to spherical? Well, I don't know my rho. Whoa, I can get it now, though. Let's do it, okay? So, can I? Yeah, I certainly can. By the way, could I have gotten it from here? Yeah, I could have, because I could have taken r. Remember, r squared plus z squared is also rho. Yeah, it's not my favorite way to get there, but I can get there that way. Well, r squared plus z squared, screw it, it is rho. So that's 289 plus 24 and a half squared plus 49. Square root that is, oh, that's not true, you dummy. Nope, clear. Try it again, stupid. 17 squared is not 2800, you goofball. That's mo better. So 30.6 would be my rho. By the way, if your rho is ever less than your, what do I want to say? Less than your r, you screwed up. Okay, that is a fact. Take it to the bank. Okay, so just be aware of that. It just feels. Yep, that's right. 24 and a half obviously is huge by comparison to the 289 and the 7. So yeah, we only get to 30.8. Now that's it is what it is, but just be aware of that. If this guy is ever less than this guy, you screwed up somewhere. Is it possible that they're very much the same? Yeah, it's very possible that that's true. So just be aware of that. They can be very similar to one another. Okay. All right, where did I leave off? Oh, this guy here. That's right. So remember that Z. I want spherical components. I want phi. So I want so Z is equal to rho cosine of phi. There you go. And remember that inverse cosine just goes between 0 and 180. So, that's why phi runs between those as well. So I want Z, which I said was 7. Is that right? 7. So 7 divide, let's do it this way. Inverse tangent. No, inverse cosine. Good night, nurse. 7 divided by 30.6. You get 76.7 degrees. Bam. There it is. There's your spherical. Piece of cake, man. Yeah, I think we do one more, just for fun. Again, the idea of needing to know this, obviously we live on our ball. So spherical components, kind of a big deal on our ball. Again, very similarly related to latitude and longitude, except remember that it's a little bit different. So for instance, let's say you had let's actually do this one. Cool. Here's our Earth, roughly 4,000 miles in radius. Oh, check it out. That right there, rho. Okay, roughly the same all the way out. Like, what about that Mount? I want to say Rushmore, but you know what I mean. Everest. Yeah. What about it? That's like 6 miles. Whatever, dude. On the grand scheme of things, it's diddly squat. Okay, well they say our world is flatter than an orange. Okay, so just be aware of that. Okay, not a huge deal. So let's say you're up here somewhere. I don't know. No, actually, let's do one in South. We'll do one in South America. Oops. We'll do one in South America somewhere, shall we? So I'm going to go ask the great Googly Moogly. Oh, great and glorious Googly Moogly. Latitude, longitude. Buenos Aires. Negative 34.6 north. Okay, now what kind of jackwagon writes it that way? That is ridiculous. Good night, nurse. That's embarrassing. You should be embarrassed of yourself. Nobody writes it negative 34.6 north, for God's sakes. Oh, that is just embarrassing. Now, the reason they probably did it that way is because there's probably something to do with, some sort of the way Excel does it or whatever. Look, 34.6. That's how a normal person writes it, but they don't write it negative. They say it like that. They say it 34.6. Now, that's actually interesting because you remember I said to you it's 90 minus your latitude in the northern hemisphere. So if you did the negative, it'd be 90 minus a minus 34, it would be 124. So I'm going to go ahead and do it that way. I'm going to say, listen, our latitude is 34 degrees south latitude, and our longitude is negative 58 degrees, or 58 degrees west, longitude, 58 degrees west, okay? Now you look at this, you're like, oh, okay, well here, 0 is up here for phi, right? And then down here is 180. That's cool. Normally we start here with our latitudes. We come here and we go down 34 degrees. So 34 degrees right there. So where does that put us? Well, it puts us at 90 degrees. That's from here down to here. Plus 34 puts us at 124 for phi. Okay? Now, technically speaking, viewed from above, and this was, this is England right here. That's 0. Okay, coming towards us is the negative direction. Okay, so coming towards us, coming toward Buenos Aires, that's the negative direction. So when we say 58 degrees west, if you headed towards, Russia, it'd be positive. Okay, and that's, again, starting from England, obviously. So you can do it a couple of different ways. Either way is fine as long as you are cognizant of where you're at. Okay. Because you can say 50, you can just leave it as 58 degrees, or you could use it as negative 58, or my personal favorite is to go 302, right? So 302 degrees would be our theta. And why is that? Well, because we went all, but 58 degrees all the way around. And then, of course, our rho is 4,000. So, wait, so you're telling me I have 4,000, 124, and no, 302, that's theta, and then 124 is phi. Oh, by the way, let me just mention this. You electronics people will always say this. Our books teach it to put phi and theta in the wrong spot. Well, you do it that way in your class, but mathematicians have always done it this way. Okay? I don't know why. Because we're weird, because you guys are weird, I don't know. You can decide who you think's weird. Now, let's do this. Can I do this rectangular components? I sure can. So x is equal to rho cosine theta sine phi. Y is equal to rho sine theta sine phi. And z is equal to rho cosine phi. Okay? Let's bust this out real quick. 4,000 cosine 302 sine 124. Sine 124 is negative. Are you with me? Sine of 124 is negative. Oops. Okay. The cosine of 302. Oh, I'm sorry. The sine. No, sine. Wait, no, I'm sorry. I lied to you. Sine of 124 is positive. Never mind. I was in my head. I was thinking backwards. Yes, so 1757. So 1757. Cool. That's our x. And then our y. If you're smart about this, you'll just come in here and change this to this. So the sine of 302, that is definitely going to be negative. So the y is going to be negative. Negative 2812. And then our z really ought to be negative because anything in the southern hemisphere is going to be negative. So it's going to be 4,000 cosine 124 negative 2236. Any bets on what those would equal if you squared them? Obviously, I'm rounding a little bit, so don't get all excited about it too much. But hey, I got 4,000. Yeah, because again, x squared, y squared, z squared added together, like plus x squared plus y squared plus z squared better equals rho squared. That's just a fact. We're going to actually have some fun with this in class when we talk about these. We're actually going to do a little experiment with latitude and longitude, and I think you'll enjoy the application. Again, we will do most of what we do in this class. Most of what we do in this class, we will do with rectangular coordinates. There will be a little bit with cylindrical and a little bit with spherical. Why? Well, because when we get to double integrals in particular, and triple integrals, I should say, in particular, what you're going to run into is sometimes you're bounded by what is, part of a sphere. Oh, that's interesting, because I'm actually bounded by a sphere. You know what a sphere looks like to do when you're trying to use it as a function in an integral? It's going to be gross, is what it is. And so instead of dealing with, z is a function of x and y and so forth, and then y is a function of x, and then, oh my gosh, what a mess. No, instead, we're going to say, listen, we're underneath of a sphere with a radius of this and such. We're going to be going from here to here in the theta direction, and from here to here in the rho direction, and that's going to be what's going to be bounding part of our stuff. So it's going to be important when we get to that in particular. So otherwise, unless you're designing something, something you're working for Garmin or something maybe, but for the rest of us, we just are in our everyday lives, mostly what we're going to be doing is walking around our flat planet, living in our box of a house, doing our thing. Okay, so not a huge deal, but just so you're aware.